The two numbers that we're looking at here, the left number in blue and the right number in orange, those are the exact same number. They're just written in a different form. Right? It'd be like if I wrote my name in just regular print versus writing it in cursive. It still says the same thing, it's just written in a different way. That's essentially the difference here between standard notation and scientific notation. And as we talked about, I think we had a Desmos activity we did, talking about like how big the sun is, how small blood cells are. Those are some kind of real world applications for when we would use scientific notation. Things that are super, super, super large or super, super, super small. All right. So this number here in standard notation, that just means the standard way we would write it, or the normal way, is 560,000. So let's go through how to convert this number into scientific notation. The first thing we need to do is define our decimal. Anyone remember where is my decimal at in this number?
All the way at the end.
All the way at the end, to the right. Anytime we have a whole number, which means not a decimal number, we know that our decimal is going to be all the way to the right. If we have a decimal number, we know where our decimal point is because it's obvious, it's visible to us. Okay, guys, stay with me, please. We can talk when we get to the worksheet, but not right now. So we define our decimal. It's right there. We're going to draw an arrow where we want that decimal to be. Anyone remember which two numbers we want that decimal to end up in between? 5 and 6. We want it, so let's draw our little arrow there right in between 5 and 6 like that. We want there to be one number to the left of my decimal. Let's write that in. One number to the left of that decimal. Because our leading number, as we see in orange here, needs to be in between 1 and 10. 1.5, 4.9, 5.6, 8.7. Those are all in between 1 and 10, and they only have one number to the left of the decimal. So we want my new leading number here to be 5.6. After that, we're just going to count the spaces. However many spaces we have to move, I'm going to move this down. However many spaces we move, this number is your power of 10. We move it 3 spaces, 10 to the power of 3. If we move it 10 spaces, 10 to the power of 10. But our base is always going to be 10, if we remember. I'll let you guys finish writing that down, and then we'll actually do it and see what we get. Thank you. So we started the decimal, we end inside that arrow, and we're going to count how many place values we need to move to end up where we want. I'm going to zoom all the way in here so we can see. We start at the decimal, and we're going to count over 1 space, 2 space, 3 space, 4 space, 5 spaces over. Does this look familiar to anyone? I see some heads nodding, thumbs up. That's good. So because we moved 5 spaces, my decimal is now in between the 5 and the 6. So my answer is going to be 5.6. That's my leading number. It's always going to be times 10. And what's my power of 10 going to be? 5. It's how many spaces we moved. That's my power of 10. 5.6 times 10 to the 5th power. So that's how we go from standard to scientific. We started out with 560,000. We got it all the way down to 5.6 times 10 to the 5th. Now let's reverse that. Let's start with 5.6 times 10 to the 5th, our scientific notation, and figure out the steps to turn this back into 560,000. First thing we need to do is rewrite just your lead number. Rewrite just your leading number. What's my leading number here in orange? 5.6. 5.6. There's my leading number. I'm going to forget my power of 10 for a second. Because now we're going to move the decimal I'm going to move this down. We're going to move the decimal the same number of spaces as our exponent. We're going to move our decimal the same number of spaces as our exponent. Something we need to keep in mind, though, if we have a positive exponent on our power of 10, do we have a really large number or a really small number? Large. Good. We remember. I'm going to write big number. And if we have a negative exponent, what type of number do we have there? Really small. Positive exponent, we got to make a big number. Negative exponent, we got to make a small number. So I have a positive power of 5 here. If I want to make a large number, should I move that decimal to the right or should I move it to the left? To the left? Should my zeros be in front for a large number? We got to move it to the right. As we saw here, a big number like 560,000, my zeros are all on the end. So I'm going to start right here at my decimal, and I'm going to move that 5 spaces to the right. 1, 2, 3, 4, 5. And make my new decimal there. What do I fill all those blank spaces in with? Zeros. 0, 0, 0, 0. A lot of times people see that 10 to the power of 5 and go, oh, it's just 56 with 5 zeros on the end. But that's not quite how we do it. The 5 indicates how many times we move the decimal space. But one of those decimal spaces has to account for the 6. And then the 4 additional ones, yes, are those zeros on the end. So now we've got 5, 6, 0, 0, 0, 0. So my answer here is 560,000. That's how we convert that number from scientific to standard notation. I wrote this note kind of small, so I'm going to zoom in on it just so we can get it down. Then we'll take a look at a couple of more examples. I'll give you a second. Yeah, Ross. Sure. All right. So for our first example, we're going to convert 7 million. Is that number in standard notation or in scientific notation? Standard. So obviously we're going to convert it to scientific notation. Where's my decimal at currently? At the very end. Where do we want it to end up? In between 7 and 0. Right in there. So we know that my new leading number in front is going to be 7.0 times 10 to the power of however many spaces we have to move. So we'll count it. 1, 2, 3, 4, 5, 6. Did I do that right? I messed it up a little bit, but there we go. 6. 7.0 times 10 to the 6th power. I messed up the bumps there a little bit, but I can fix it. Looks slightly worse, but that's okay. 6 spaces over, boom. My power of 10 is going to be 6. Now if we have something like 0.0000997, where's my decimal at in this number? Right there. We can see it. We don't even have to draw it in because we can see it. Where do we want it to end up? At the end? Not quite. We want one number to the left. Not between 9 and 7, because then we'd have 2 9s to the left. We want it in between the 2 9s so that we have 9.97. 9.97 times 10 to the power of however many spaces we have to move. So let's count it. We got 1, 2, 3, 4, 5 spaces. So I've got 10 to the power of 5. Yes? Does that look right?
Yeah.
What am I missing? Let me ask you this.
Oh, negative.
A negative? Should the 9.97 be negative?
No, the 97.
Which part of this should be negative? The exponent of 5. How do we know that we have a negative exponent here? Very, very small number. Right? If I offered you $7 million, or if I offered you $0.0000997, which would you rather have? 7 million. This is a super, super small number. When we have a very, very small number, we have to make sure that our exponent is negative. Small number equals negative exponent. 9.97. Again, that leading number is in between 1 and 10. Right? 99.7 is not in between 1 and 10. But 9.97 is, just barely. What if we have, let's do from scientific to standard real quick before we talk about some proportionality stuff. I'm going to move this down. What if we've got 5.21 times 10 to the negative 2? Am I going to have a large number here or a small number? Small number, how can we tell? Because the exponent's negative, good, so that's a small number. Are we going to move this decimal to the left or to the right?
Right.
To get a small number, think about it. To the left, right? We want the zeros in front, just like we had in the previous example. So I'm going to rewrite 5.21. And I'm going to move this decimal 2 spaces to the left. 1, 2, boom. Fill in that blank spot with a 0. What number should we put to the left of my decimal? 0 as well. So my answer here is 0.0521. Can we just drop off the 2 and the 1 and call it 0.05? No, absolutely not. Every single non-zero number, okay, which means any number that's not 0, obviously, has to be included in our answer. We can't just round up 9.97 to 10 or to 9.9. We have to include every number that is not 0. So if it's 5.21, we've got to include the 5, the 2, and the 1. I got to flip over, so I'm going to leave that up for a second. That's all we're going to talk about for scientific notation, though. We're not going to worry about multiplying and dividing in scientific notation. I don't want to include that. Yes? Can I move it up? Sure. All done? Perfect. All right, let's talk about some proportionality here, shall we? Starting off with the constant of proportionality. Getting into Unit 3 now. Unit 3 was our last blue unit. Looks like this. Right? Talking all about oh, this was a long one. We're talking about proportions, slope formula, slope and y-intercept, all of our favorite things in the world. Starting off with the constant of proportionality, which is, of course, k is equal to y over x. Something we didn't get to touch on the first time we learned this lesson because we hadn't really talked about slope yet is that k is just m. It's the same exact thing, except k is exclusively in proportional relationships. So that's a straight line through the origin, whereas m, our slope, we can find through non-proportional relationships as well. Straight lines that don't go through the origin. Where a constant means repeating over and over. And the phrase that we learned here with this, anyone remember? It's not Yo Mama's ex-boyfriend, it was something else. Here we go, exactly. Why aren't you over your ex? Because to find k, we put y over x. Y over x. So if we want to find k, we can have a table that looks something like this. Where my x is on top, my y is on the bottom. And we could say that I've got x values of 1, 2, 3, 4, and 5. And I've got y values of 4, 8, 12, 16, and 20. If we want to find what k is equal to here, all we have to do is focus on one single point. I'm going to take this very first point because I like that x value of 1. And I'm going to plug it into y over x. So in that purple point that I boxed up, what's my y value there? 4, thank you. What's my x value? 1. What happens when we simplify 4 over 1? What do we get? 4. So k is equal to 4. Now again, we didn't get a chance to touch on this the first go around, but like I said, this is exactly the same as slope. So if we wanted to, we could do the change in y over the change in x. The change in y on the bottom. How do we get from 8 to 12? Plus 4. How do we get from 2 to 3? Plus 1. Right? M would then be equal to, like we said, the change in y over the change in x, which is positive 4 over positive 1. Which also equals 4. So we didn't spend a whole lot of time on k, finding the constant of proportionality, but we spent months talking about how to find m. So if you're confused on the difference between the two, literally just find m. It's like the old square and rectangle kind of relationship, where a square is also considered a rectangle, but a rectangle is not necessarily always considered a square. Do you guys know what I'm talking about?
Yeah.
Some of you do. Good. So K is always the same as M, but M is not necessarily always the same as K. Hopefully that makes sense. In this analogy, K is the square, M is the rectangle. Because you can find the slope of a proportional relationship or a non-proportional relationship, but you can only find K in a proportional relationship. I feel like the more I talk, the more confused we get, so I'm going to stop. But that's how we find K. Now we're going to draw. I didn't have time to print out, and I didn't want to hassle with the glue and everything like that. But let's draw a quick little graph here. Oh, good morning. Thank you. Quick little graph on the X. We're going to have, let's see, what should we have? One, two, 3, 4, 5, 6, 7, 8 on my x-axis. Then on my y-axis, I'm going to have the same thing. 1, 2, 3, 4, 5, 6, 7, 8. Make 3 points, one at the origin, one at the point 2, 3, and one at the point 4, 6. Let's take a look at how those graphs look real quick. Make sure to add in the actual coordinates because our graphs don't look super precise. We'll get some glue-in graphs later this week though. So we can find K from a graph just like we found it from the table. All we got to do is take y over x. I'm going to pick this point right here, 4, 6. Let me zoom in. All right, 4, 6. Which of those numbers is my x coordinate, 4 or 6?
Oh, no, 6.
X coordinate.
Oh, 4.
X comes before y just like in the alphabet. There's my x coordinate and my y coordinate. So K is going to be equal to 6 over 4. If we remember, 6 is just 2 times 3. 4 is 2 times 2. What can we cancel from the top and bottom there?
2.
The 2's.
3 over 2.
And that leaves us with an answer of 3 over 2. That is my constant of proportionality from this graph. But again, K is the same as slope. So if we wanted to, we could find the slope of this line by doing rise over run. From this point to this point, how many units do I have to rise?
Oh, no,
1, 2, 3. So my rise is 3. How many points do I have to run over?
4?
Count the squares.
2.
2. Is that the same that we got from doing our K? Yeah, 3 over 2. All right, we're going to end it there. Finish writing that if you're still writing that. And we're going to get F02. Shouldn't take super long. We've got 20 minutes.
I'm so tired right now. You're still
What?
recording.
Yeah.
Church, you're still recording.
Oh, thank you for letting me know. I'll turn it off.
There's